slide is also visible, sir.
Yeah. Thank you for confirming that.
Okay, sir. Thank you, sir. Sir, we will start in another 2 minutes, sir.
Yeah, we'll be waiting.
We'll start with the welcome address and then we'll go ahead with the scenarios of yours, sir. Thanks, sir.
Okay. Thank you.
A very good evening to one all present here in this virtual gathering. It's time to welcome our chief guest. It's absolute pleasure to extend a warm welcome to all to this ATAL FTP program, and we are gathered here today to engage and enrich learning experience, fostering innovation, knowledge sharing, and professional growth. Mr. Sukumar Balasubramanian, currently serving as a senior manager PCB design at ATAL Semiconductor Private Limited. With over 17 years of experience in PCB design, he had the privilege of working on a wide array of innovative projects, each of which has strengthened his expertise and passion for this field. His academic journey began with a bachelor's degree in electrical and electronics engineering from Dr. Mahaling College of Engineering Technology, which laid the foundation for his career in electronics and design. Beyond technical expertise, he is also a certified internal auditor for ISO 9001 2015 and an active member of our quality management team, ensuring that we consistently maintain high standards in the design. Now, I request our beloved chief guest, Mr. Sukumar Balasubramanian, to continue his session. Sir, please.
Hi. Good evening, everyone. Thanks for my introduction. So thank you all for your time in joining this session. So as our said, right, so I'll be going to the next 1 hour we are going to have a higher details on high frequency PCB designing. So what is the PCB designing? Let me share my slide. So we are going to see about the high-speed PCB designing. So which will have the usage in the electrical vehicles, right? So I think they have already introduced about me, right? So I need to add up on that. So I'm proud to say that I'm the first batch of the EEE department from the Mahalingam College. So these are the today's agenda. So you can use the chat box if you have any doubts, right? No, if you have any doubts, you can just drop your text in the chat box. You can use the chat box for that one, right? So what are the agendas, right? So what is the PCB, right? The set of people, right? Few may already know about PCB. Let me know how many of you have some idea of PCB. So I'm waiting for a text in the chat box. Do anyone already know about what the PCB is, right? Some basic ideas. Okay, so let me see about what is PCB. It's a printed circuit, and what are the key elements in this PCB, and what are the importance of the high-speed printed circuit boards in the EVs. So how they are important for in the EVs, right? So next, what are the types of PCBs? So I have categorized PCB into two types. So we'll go on that one, what's the type of PCBs, and then the high-speed PCB designing challenges. So what are the challenges for us in designing the high-speed PCBs, right? So this is the today's agenda. As I already said, if you have any doubt or clarification, you can use the chat box. If you have any questions right away, you can just drop a text in the chat box. So let's go to the next slide. So what is a PCB? It's a printed circuit board. It's nothing but a transmission lines, a collection of transmission lines. So the PCB will have the connections, the destination to source to destination, there will be a wire connection, right? So similar fashion, we'll have it in the smaller PCBs. So if you go on to the definition of the PCB, it's a laminated structure. So I have a conductive layer and then insulated layer and then a conductive layer. So this is a laminated structure of conductive and insulated layers. So this is the PCB, how the PCB looks. I think most of you have seen at least a PCB which is used in your laptops, in your TVs, in your mobile phones, and in all the electronic gadgets, we are using the PCB. Without PCB, there is no electronic gadgets, right? So the green color board you have seen. So that is called as the printed circuit board. Here, the types of PCBs, we have based on the application where the PCB is going to be used. Depends on that application. We have one-sided copper, one-sided PCB, that is the conductive layer will have only one side. So double-sided PCB is will have the double sides on the top and bottom layer, both have the copper material, and then it's isolated by the insulated material. And now we are using the multi-layer PCBs. So multi-layer is, we have used up to 80 layers, 64 layers, 74 layers, like we are having the PCBs. So let me go and see in deep how a PCB and what it has. So next, what are the elements will be in the PCB? So the PCB has, as I said, right, electrical connection. We call it as traces. So we call it as traces. The traces is the electrical line. It's basically a copper which connects two nodes. You can see in the picture, right? So this end-to-end connection, these are all called the traces. And next, the via. What is a via? So via is, as I said, right, there is two, if we go with the multi-layer PCBs. So top and bottom layer. Both layers will have connectivity. So if you need to take a signal from the top layer to the bottom layer, you need to use a via. It's just a vertical conduction, right? So there are types of vias, and what type of vias we are going to use depend based on the requirement. We will see in deep in the next slide coming slide. So what are the next to the copper planes? So what are the copper planes? Say, yeah, as I said, right, it is like a trace. The trace is for used for the low current applications. If there is a high current application, you can't able to just, you can't not just stick with these modern lines, because you need to have more copper to have high current application. So for that, we are using a technique called the copper planes. We will just float this copper. So this is called a copper plane. So next one is the layer stack-up. I already said, right, it's a laminated structure of the conductive and insulator layers. So how these structures were arranged? So we have a core and a prepreg. Core is nothing but a non-conductor material sandwiched between copper foils. And then prepreg is a non-conductor material. So copper weight is how much copper weight you are taking for the film. So these are all we will look into in detail the copper plane, what is the VR trace, and then layer stack up. So I'm just giving a basic information of printed circuit board so that you guys can understand what a high frequency PCB circuit, what are the challenges, right? So that's why I just added this few slides for your convenience. So this is the VR structure. So we have a through hole VR. So through hole VR is if we have a 6-layer PCB. Here we have a 6-layer PCB design. So to take a signal from top layer to bottom layer, and also it connects to all the inner layers, we call it this as through hole VR. So it basically travels throughout the board. If it is a blind VR, it starts from top layer and ends in some of the internal layers. It won't come to the bottom layer. So this depth is depends upon the application, and this signal parameters we can decide to up to which layer it need to be traveled. So this is blind VR. And then buried VR is it doesn't show up to the external layers. It started in the inner layer and then finished in the inner layer. So these are the buried VRs. And micro VRs is a smaller VR. It's just how to top and then to the adjacent layers that will be used in the high definition interfaces. We will use those VRs. So why we need this VRs? I already said, right, for the connecting from the one layer to the other layer. So other than this, these VRs serves for the thermal and mechanical stabilities. So how it is used for thermal? It uses for the if you use a VI in a particular fashion and a particular signal, then it will take care of the thermal dissipation, heat dissipation. So based on the application, and we need to wisely use those VRs for the heat dissipation. And then to maintain the physical strength, mechanical strength, like based on that, we work with the mechanical team, and from their suggestions, we'll use those VRs wisely wherever is needed. Also, for the high-speed signals, right, we need to maintain the constant impedance. So these VRs we need to place to match the impedance of the transmission line. See, your traces will be designed with the 50 ohm impedance or 90 ohm impedance based on the interface. Say if you are using a 50 ohm impedance trace, and the VRs used for those traces should have a 50 ohm impedance control. So it will be achieved by the VR size and then pad size and the copper plating in some inner walls of the VRs. They will decide the impedance of this trace. So that's the VR stub. The VR stub is nothing but the extra copper flow which exists in the PCB that we are not using. So for example, this is a high speed trace. This signal starts from the top layer and ends in the third layer or something. So this extra length is right, we call it as stub length. So it will be act as an antenna that will call out unwanted signals, right? So we need to eliminate that one. So to eliminate that unwanted stub length, we are going with the two techniques. One is called, we are using this as a blind via so that the unwanted stubs will be reduced. Other technique is called as back drilling. So back drilling, what is that one? We will use the through hole via and then we'll route it and as it is, and this extra stub will be drilled out and then it will be taken off. So these coppers will be drilled out. So that is called as back drilling technologies. So this is the via structure and what are the types of vias. Do you guys have any doubt up to this one? Okay, then let me proceed to the next one. So this is the layer stack-up. So layer stack-up is nothing but, as already said, right? It's a copper layer and then a non-conductive layer and then a copper layer. So it's the typical 6-layer PCB structure is shown here. So likewise, we can design up to more than 50 layers, 60 layers. So I have designed about 78-layer design for one of my Intel projects. So the top layer, it's just a copper, and then the mid layer, this is called a core, which has the copper and then a pre-plug in between, and then the copper. So what are the constraints or what are the things we need to take in care while designing a layer stack-up for a PCB? So it's basically depends on the application where we are going to use that PCB, right? So based on your application, what are the types of signals you are using in your PCB will altogether we need to consider while constructing a PCB layer stack. For example, if for our case, we are designing a high frequency PCB designing, right? So high frequency signals would be routed on maximum. We try to route it on the external layers. We should use only the external layers for the high speed signals because the external layer will have it. We will have the full efficiency of that signal because the dielectric medium is air. So we need to go with the external layer. And if you are, there is no other way. If there is lot of signals, then you need to go to the inner layer for your high-speed routings. Then we need to take care of certain things. So that we will see in the upcoming slides. So what are all the constraints or things we need to take in care while routing on the high-speed PCB signals? Okay. The layer stack-up should be symmetrical. Symmetrical in the sense, if you bisect the layer PCB into two in the mid, then the layer arrangement from the top layer to the mid and the bottom layer to the mid should be symmetrical. And the industry standard says that we should design only the even number of layers of stack. This is why they need to have the equal. It will be useful in the mechanical stability, and then the signal arrangement also should be taken care while designing all those things. If we have a mixed signal design, if you have in your design, you will have the digital signal, you have the RF signal, if you have the analog signals, then the analog signals should be on the other end. Say if it is in the bottommost layers, your digital and the high speed signal should be on the topmost layers. So that you can split up you can give isolated the analog and digital signals accordingly. Not only in your single layer, you have to isolate your analog and digital signals all the way through the PCB. Whenever and wherever it is needed, we need to isolate the analog and digital signals in the PCB. So that we are going to take care from this stack-up arrangement itself. Also, the stack-up layer, the layer stack-up, if we are using impedance, or if you are using a high-speed signal, you should maintain a constant impedance for those signals. So if you want to maintain a constant impedance, the impedance will be achieved on based on your dielectric thickness and then the material, board material. So it's the dielectric constant and then the copper thickness. So how many width, in which width you are routing those traces and on which copper base. All those will be considered while calculating the impedance of that particular trace. So here the dielectric thickness and then your impedance trace width all should be taken care while constructing your layer stacker, right? Okay, let me shoot a down question for you all. So what are all the, do you think in which areas in the EVs we are going to use this high speed PCBs? So in our EV, right, we have a lot of systems. Say you have a parking sensor and collision control system, like that we have some. So in all those things we will be using these PCBs. So if you take a EV vehicle, so these are all the more important sensors or the systems, right? The parking assistant, rear collision warning, blind spot detections, and your look around rear collision warning, and braking assistance, very important, collision avoidance. So all these systems will have a particular, they will have their own processors. If you take a single system, if you take a brake assistance, it has its own parking sensor. So that's sensor and the processor. So processor will be always sitting on the PCB. You can't go and you can't go and solder or connect a wire directly to the processor. It should be always on the PCB. So your connection or your signal from your sensor should travel to the processor without any noise or without any disturbance. So all these are taken care only in the your high speed PCB design. So in your PCB, it's all should be taken care. Otherwise, these systems will not, or these sensors will not work properly. Right. So for the efficient function of your system, the system I call it each and every system, braking system or everything should work efficiently only if you have a high quality, high frequency design. If your PCB design has some issues, or if some of the things we have not taken care in the PCB, then the actual system, the whole system will not work as we expected, right? So that's why this high speed PCB is very much important in the electrical vehicle, right? So for example, we have a battery management system. So here we need to monitor the state of the charge and then temperature and overall health and the safety along by providing the real-time data and control, right? So the real-time data and control will only possible if you have a good PCB in your system. Same way in the communication system also, now our cars are coming with the effective communication systems, right? The communication system is not only the communication from the control unit to various part of the EV systems, right? So your central processing unit, the signal should be received. So all those things will be connected through the PCB. The more importantly, ADAS, right? So here the radar system in the ADAS is operates with 24 gigahertz to 84 gigahertz, right? So your PCB, it's used in the conventional radar system. So your PCB also should meet all these frequencies when you've taken care of those particular signal routing or during those connections. Okay. So likewise your informating system, also navigation system, and then your entertainment system. So these are all things. So let's come to the types of PCBs. So there are two types of PCBs. So one is application board and then the test board. Application board, you all are aware of that one, because application board is just nothing, just a PCB that is used in the actual your electronic device, actual product. So say if I'm saying a cell phone, the PCB used in your cell phone is an application board. So that board, say it is a typical application board. So the PCB will have their ICs and their resistor, active and passive components, right? So let me take this IC. So it's the function of this IC is depend on based on the system. So in your application board, you are directly using this board in your application. The second one is the test board. So what is the why we are going for the test board, right? So here you can't use this ICs directly into the system without testing this device. If this device is working 100%, right, without any errors or fault, then only your entire system will be work perfectly. So before using these ICs in your actual system, we need to test the functionality of these ICs. So there comes the test boards. So the test boards will have the board where this actual application is using. The ICs will be tested on the actual environment. Say if we are using in the for a defense sector, so in which climatic conditions, so it's say minus 35 degree to 150 degrees Celsius. So these ICs will be tested under those conditions, and what are all the inputs and what are the outputs expected from those ICs. So those will be designed in a separate board, and then we will, it's just like a simulation, but it is not actual simulation. It's not just a simulation. Actually, we are operating the device and we are giving the input and then measuring the output and then testing those ICs. So I'm expertise in designing such test boards. So all the ICs which we are using in our electronic devices, say in our phone, if Samsung or some other brand is releasing a 5G chip or some other chip, right? So those will be tested before releasing into the actual product. So those test boards we are designing. So what we need to take care in those test boards? So what are all the things we need to take care in the actual application board? All those things we need to do in our test boards, right? So that's where we are using the test boards. So in which stage we are testing these ICs? So we are testing those ICs in two different levels. So one in the wafer level before packaging and in the after packaging and the device level. So we call it as the wafer level testing is called as probe card and then dead boards, device under test, right? So we have designed high complex RF boards with 68 layers boards with micro and blind vias. So in the right side, you can see the silicon wafer, and then they have a circuits which is memorized into this one. And after that one, this wafer is tested before packaging into the actual device. So it will eliminate if say if there is thousands of wafers, right? Each and it's a silicon and each one is called as die, right? So without testing, if you package, then after packaging, if the device is failed, the packaging cost and the expected amount of devices that all will have a big impact in the production. So in industry standard, we used to test the device in wafer level and in after packaging. So each and every ICs which we are using in our real-time application will be tested, and they will be put it into each bins. If we have to test those ICs for 20 tests, open circuit test, short circuit test, and then there is list of testers there. Those or a device would pass all those tests in a particular range of measurements. If that all the tests were passed, then they are called as the first quality IC devices. So they will be separated in a particular bin. Right. So this is where we are using the test boards. So I hope you are clear about the application boards and the test boards. If you have any doubt or do you have any clarification on the one, please drop a text in the text box, or you can unmute and ask me. Okay, then we'll move to the next. So what are the challenges we face as a PCB designer, in particularly in designing the high-speed PCBs? So as I already said, right, the design, your PCB design is the most important one in a system to fulfill its requirement. So it's very important to know what are all the things we need to take in care during designing the high-speed designing. Okay, so first we'll go with the component selection, and then what are all the types of interface connectors, right? The USB and HDMI slot. So those are all the common known high-speed interfaces. So if we are using a HDMI, right, then what are the things you need to take in care? So once you plug your HDMI cable in the slot, the signal transmits from your screen to maybe your PlayStation or something, right? Your set-top box. So how the high definition signals will be transformed into your display. So from this cable to your display, there is an interface which is a PCB. So once the signal is transmitted from the cable to the connected jack, from there the signals will be taken care by our PCB. So in what impedance your cables are designed, so you must have those similar impedance in your PCB also. So there is certain rules and there is lot of constraints when using the interface connector. So it depends upon the which interface connector you are using. So there is the recommendation in your connector designing itself. You can have those informations. So what are the things we need to take care in our PCB? And then the placement of the component. So where you are placing the component. So the processor will be placed in a particular place, and then next to it, what are the things need to be in the priority position, and what are the things you need to be placed on the edge of your PCB. So if you have an edge connector, those connector you should be placed in the edge of the board. If you can't place it in the center of the board, right? So that is basically for the assembly or usage. Other than this, your signal integrity. So how your signal is acting. So what type of signal you are using. So based on that, you need to place those components wisely. And then as I already said, right, via structures. So based on our application, we have to use those vias to conduct your signals from one layer to another layer. And then most importantly, routing of the high-speed signals. So what are the things? The routing is just about drawing the trace. So drawing a trace, we call it as routing, connecting the two nodes. So the trace which carries the high-speed signal should be treated very critically. How without those trace, the other signal should not interface in it, and then the noises in the signal should be reduced on the way, and then the transmission loss also should be taken care, and everything we need to taken care while doing the routing. And the layer count and layer structure and the board thickness. So board thickness basically in which application you are using. Say you are for the cell phones, right? You can't go with a bigger board thickness, right? You have the limitation there. So likewise, in which electronic devices you are going to use those PCB. So based on that, your board thickness and the number of layer counts will be decided. Finally, the PCB material. So what are the how we are selecting the PCB material? In case of for example for our high speed designing, we need to take a PCB material that has dielectric constant value less, like that. We are having some parameters. We'll go through this on in detail. So component selection. So how your component is selected? The first importantly, if you are using for a high frequency circuit, then those components would be appropriate and supportive to those high frequency level. So that's the first thing you need to take in care while selecting the component. And then, as I already said, the impedance matching. So this is to reduce the reflection and the signal loss, and those components will have certain impedance. The components itself designed for a particular impedance. So we need to look on those impedance data and then use those component wisely as per your requirement, as per our requirement. And then the power integrity, right? So we need to go with a good power supply rejection ratio and then low noise and low loss, right? So everything we need to take in care. So those data sheets, the component data sheet is the more important. You should go through the data sheet thoroughly and how to pick up those components based on our requirement. And then the thermal management. So temperature rating. So at what temperature our PCB is going to work? Say if our PCB is going to work at maximum of 150 degrees Celsius, then the components used in those PCBs should have the temperature rating should withstand at least 150 and above, right? So you need to go look at the thermal rating. And as I said, right, the components should have the minimum electromagnetic interface and electromagnetic capabilities. So all those things you need to take in care while selecting the component. And more importantly, component availability and reliability. If you select a component that should at least should have for next few years, you should select the component manufacturer. You should just go through the background of that manufacturer so that they can able to supply those components for the next few years. At least we upgrade our system, right? Because if you are running in the production, if you don't have that same component, then you have to use a different component with the different parameters, then your results may differ. So you should select the component availability right now for the next, considering for the next few years also. And as a engineer, right, we need to give a low cost product to the customer. So we need to select with the budget friendly. So we need to look into the component cost. Based on that, your entire budget will get changed, right? So say if you have a component, maybe a zero point 0.1 microfarad caps with 1% tolerance, right? 50 volt, it works on 50 volt, right? So if you have two manufacturers, so one manufacturer is giving you high price and another manufacturer is giving you low price, then you should, as the parameters are matching, we should definitely go for the low cost product, right? So that's also we need to take in care. So these are the criteria, are the things we need to consider while selecting our component that is used in our PCB design. So the next one is interface connectors. So I just go show you some of the interface connectors that we use. So you all know that universal serial bus USB connectors. So other than that, Thunderbolt, HDMI, PCLE, and then SATA is used in your systems, right? Ethernet, you know, for the LAN connections you are using that one, and fiber optic connectors, M2 point, M.2 and U.2, display port, quad small form factor pluggable, and then your high speed data HSD signals and FACTA connector, slim stack, automotive Ethernets, micro lag connector, high power connectors, right? So these are the different types of interface connectors we are using in our PCB. So where it is used, so as I said, right, we have two different systems. One may be a sensor system, and then another may be the central processing unit. So these two will not be connected throughout the PCB, right? It will be in the other one end, and our central processing unit will be at the other end. So these two signals should be connected through a cable or something, right? So the cable will have the interface connectors. So these interface connectors were used more or less all the devices will have those interface connectors. So only thing what we need to take care is when designing a PCB and using the interface connector, what are the things we need to take care in our PCB that is recommended in the data sheet of those connectors. So those would be taken care in our PCB design. So next we comes for the component placement. So you have a PCB, as I said, right? So you have a different components. While designing the PCB, a designer engineer will have the question where to place this component and which component should be placed near which component, and what are the impacts if we place it further away or closer by. So all those things, right? We need to look into detail. So if for any system, there will be a central processing, maybe a central main integrated circuit. All those circuits, all other components will be a part of the or the supporting for that ICs, right? So the component placement will be depend on the particular IC and its operations and what are the types of signals that carried in and through to that particular IC. So in the picture you can see that, right? You can see just on IC, and there is a lot of discretes placed around, and then relays were placed here. So this is where that this is just a component placement. Sorry. So when placing a component, as a designer, we should know how to minimize the trace length. So it is directly affects the signal delay. Excuse me. Sorry. Okay. So where we left, the trace length. If you placing the component further apart from each other, then the trace length will get increased. Once the trace length is increased, there is a signal delay, and there may be interface from the other signals, coupling, right? Unwanted noisy couplings will. There is a lot of chances. So we need to minimize the trace length by placing the critical components all together closer. Also, it will reduce the board area. So nowadays we are making the things very compact, right? So when the things become compact, we need to place the components our PCB should be, our PCB area should smaller, right? So we need to place all the components as close as possible, and it should be in a compact manner. Not only in a compact manner, it should give the to our traces, right? So what is the signals we are using? It should satisfy the parameters for the signals, not just merely placing the components all together closer. It should also follow the signal path and pattern. And the clock sources, that also should be positioned in the central. From there, the signal should travel to the other systems. So if we place a clock signal in a particular space and then the receiver data signals in the further end, then there will be clocks too, right? So they will not be in the synchronized. So the signal timing and everything we need to taken care by placing the clock source in the middle of or the central position of those processor. And the power supply to the particular device or IC, integrated IC, is more important because the power supply should be constant. Should not be any fluctuation, and there should not be over voltage, right? So, and the signal should not be noisy. So all those things we need to take care while placing the component. For example, for a IC, if you are giving a power supply and you need to provide the decoupling capacitors near the power pins of the ICs. So what is the role of the decoupling capacitors? It will reduce the noise, unwanted noises, it will reduce it. And the bulk capacitors, you need to place it in the source where your supply is coming from. So what's the role of the bulk capacitors? So it will avoid the fluctuation. It helps to provide the constant voltage to our device. So those things will increase your lifespan of your device. Right? And in some of the areas, we will use the heat sink where your processor getting overheated, especially in a high speed process, right? They will get overheated. To reduce the heat, we will keep the fan and other hardwares in the system, right? So that is for the entire system. For a particular IC, will have a heat sink. The heat dissipation will be taken care on that particular place. Instead of having a external fan or something, right? So we will have the heat sink also. So these are all the things we need to take care while doing the placement. So the component data sheet, what are the recommendations given in the component data sheet should be gone through and be taken care in before while doing your PCB placement. Is that clear? Any questions? So are you able to follow up, right?
Questions in the chat box.
Yeah.
Just drop the questions on the chat box. We will be just conveying it to the resource person so that he can just reply to your answers, questions.
Yeah. If you have any questions, please use the drop box, chat box, right? So let me move to the next station.
Mr. Sukumar?
Yes, sir.
Yeah, Sukumar, I just have a doubt. So you said that impedance matching, right?
Yes, Suresh. Sam Suresh,
So,
right?
yeah, yes.
Yes.
So suppose we have two components, both are matched with 50 ohm impedance. Then
Okay.
how we will connect the components? Because both components are literally matched for 50 ohm.
So you need to connect those two components, right?
Yes.
That's for your question.
Yes.
Yeah. So you have to design a trace that should have the same impedance, say 50 ohm, right? So what are the things we need to take care is that the trace width, and then on which copper base it is sitting. Maybe it's on a 0.51 copper base or 1 ohms or 2 ohms, right? So that is basically copper area. So how much copper you are using for that signal to connect two traces. And then there is a dielectric thickness. That is the distance between the next adjacent layer. So there is a formula for that one. So in that formula, you have to implement all those things. There is a tool for calculate those one. With the tool, we will achieve these parameters. So the trace width, and then the dielectric thickness, what we need to use, all those things will be we calculate using the calculator, and we have a separate formula also. I can share you that formula later, right? You can go through that. I'm answering your question.
It's fine, but all these electromagnetic effects,
Yeah.
will it limitation while designing these transmission lines?
Yeah, there is a limitation. In the next slides, right? We are going to cover the routing stage. So what are the things we need to take care while doing the routing of these signals? In those slides, you will discuss in detail.
Fine.
Yeah.
Thank you.
Yeah. Thank you. So this one we already seen this one, the VR structures and what are the types of VRs. So here comes our most important part, right? The routing of the high-speed signals. So as we all just now discussed that the controlled impedance. So your signal should be on the controlled impedance version, and then the trace length matching. So you need to match the clock and the data signals, right? So if you are using a multiple devices on the similar operation, that those systems should match with this one. So to minimize the crosstalk, and then while routing a trace, you should avoid 90-degree bend. So right, if you are connecting these two traces, we are not using any 90-degree bends. We are actually using the curved types of signals or a 45-degree bend. So this will give a signal for the smooth transaction. If you have a 90-degree bend, then here there will be issue in transmitting the signal from here to here. There is a signal reflection. Some issues will be occurred when you use a 90-degree angle bend. So we are always using a round cornered traces for the high speed signals. And then the solid ground plane. So each of your signals should have a reference ground plane for your return path. So without a ground plane, right? All the signals should have a return ground path. And via usage for the high speed signals, you better avoid using the vias because it will create unnecessary stub and then signal delay, and your conducting length will get increased. So you need to avoid the vias. If there is no other way, we need to use the vias. For example, in this case, these signals we can route it without vias, but from this pin to these pins, we should have to have a via to connect those things, right? So in that case, what type of via we are using? We are using a blind via, or we are using through-hole via with the back drill operations. So those things we need to take care. So we need to use the different types of vias. What I have shown you in the previous slide, based on your application. So differential pair routing, the positive and negative signals, we call this as differential pair routing. So the trace length and the trace travel pattern should symmetrical and should match with the P and N signals. So these are the constraints we need to take care while using the while routing the high-speed signals. So to answer your questions, right, while we doing this routing, to avoid the unnecessary electromagnetic inductions or other analog signals or other, right, we will use some techniques. So we will see in the next upcoming slide. So what are the techniques we are using in that? So one is stitching vias. We are just not routing those signals. We are using stitching vias which is connected to the ground. So these signals will be covered on in between the ground planes, right? So on the surface, these traces will be sandwiched by, this is a ground plane, this is a ground plane, and these signals will be routed here. And in the layer stack up also, the next layer is should be a ground layer. See, if we are routing the high speed signal, then next layer will be a ground layer, and then we'll have another signal layer. Or if you are using the inner layer, if you are routing this as a signal layer, and this layer should be ground layer. So all impedance traces will be sandwiched between two ground layers, right? So these things will help in our maintaining the signal integrity, and then it will give a low impedance return path. So we can ensure a stable communication by using these stitching vias. And this is also used as the EMI shielding, as I already said, right? So it will protect the sensitive signals from the external noise and reduce crosstalk. So this type of techniques we are using. So this is a interface connector, right? So from there we are going in connection to a processor or somewhere. So this stitching vias will give the, also the stitching vias will act for the thermal management. As I already said, right, the high speed traces will always be on a higher temperature, or it has the property to have a higher heat temperature, right? So this heat will be dissipated through those stitching vias. And also these stitching vias were connected to the ground plane. So which gives a proper grounding. So it will, then and there it will reduces the noises from the other external sources. So this is one of the technique we are using to maintain a high speed signal without, to avoid the EMF effects, right? So this is another technique, but it is rarely used one. We are giving a board cutout, right? So we are, instead of just separating it from a ground layer, we are just adding a board cutout, so that these two different signals will have, maybe here we have analog signal, here we have a digital signal. So if you add a cutout or something, then it will isolate the high speed signals from the other signals. So it's also sounds the same as like the stitching vias, but it's in a different way, and it's based on the application. We are not using it in all the boards, but if it is really required, then we are going with this technique, board cutout. And while doing the length matching, we need to take care of certain things, that the loop width, right, it should be the 5x spacing of your trace width. Say if you are using 8 mil trace width, you have to at least give 40 mil between these two to avoid the signal jumping, those issues. And then you need to maintain distance between these two at least 3x spacing. So if we are using 8 mil, we need to at least go with 24 mil between this trace to trace, right? So there are some industry practices which depends upon the applications, but in general, we will go with those things. And then what is the percentage of impedance we can achieve? So we say I have designed it for a 50 ohm trace, but in actual practical after manufacturing it, the trace will not have 50 ohm. It will have some certain tolerance. So we need to provide a tolerance limit. For 50 ohm signals, we are giving 10% tolerance. For 100 ohm signals, we are giving 5% tolerance. So based on that, the fab vendor will achieve those impedance on those traces by adjusting their dielectric thickness and their material. They will achieve those things. So layers checkup, I think we already discussed on these things. If you have any doubt in that, just drop a text in the chat box. I can answer your questions. So here also we are using those vias wisely to achieve our lossless system. And last but not least, our PCB material. So PCB material is nothing but the dielectric material. So one is the copper, another is the dielectric material. So the copper sits on the dielectric material. So each and every trace or copper we are using for the signal transmission on the copper base will have the direct impact on the what type of material we are using as a dielectric medium. Right. So in industries, there are a lot of dielectric materials. There are a lot of PCB materials available. You can go through and then you can explore what are the materials available. I can show you few of the materials which are used for the high-speed RF boards. Right? It depends on, yeah, on the material availability also we should need to take in care. If you design a PCB design by considering a particular material and its properties, the material properties is their dielectric constant and then their thermal glass transition temperature level. So all those things you need to take in care. If you design a PCB by considering those material, when it comes to the production, if that material is not available, then you need to entirely, your parameters will entirely will collapse. So you need to take care them as like the component, your PCB material selection should also wisely be selected based on your application and the availability in the market. So for the high speed application, you should have a lower decay values and your lower DF values, the dissipation factor will have a low signal losses. And for more importantly, the thermal properties, I told right, glass transition temperature, TG values. So you should select the TG values based on your operating temperature. And the impedance control, right? What's the speed of your signal you are using? So the PCB material will have all those things. So these are the few PCB materials we are using it for our RF applications. So these are all from Roger and these are all from Isola. These are manufacturers and they have their different materials. FR4, they have the different DK values and their TG values. So you need to select your material based on this one. Okay, do you have any other questions? I think the PCB material is our last section. So from that one, I think we came to our end of your. If you have any questions, we can discuss it, or you can have it on your chat box.
I request the participants to kindly post the questions in the chat box. The session is open for discussion.
So I hope you have learned something new in this past 1 hour, which you are not aware on that one. Few maybe already know about all these things, or few may not. I hope this will be this has a useful session for you all.
Hello.
Yes.
Yes, Venkatesh sir, please.
Sam sir, you may ask a question.
Sir, no doubts, sir. So you can continue.
Sir, thank you for the clear presentation, sir. I hope
Okay.
this informative session for all the participants. Sir, we are really proud that you are the first batch of Triple E as an alumni
Yeah.
interacted with us for the last 1 hour 10 minutes. It was really an eye-opening session for each and everyone who is working on PCB, sir. So thank you very much, sir. Thank you for accepting our invitation for providing this lecture on high-speed PCB designing.
Yeah. Thank you, Venkatesh, and our college team for considering me for this and giving me these opportunities to just share my knowledge or something what I learned in my career. So it's really give me some satisfaction for me. And thanks again for all the participations for your time. Thank you all.
Thank you, sir. Thank
I request the participants to kindly fill the feedback which is posted in the chat box. The link is being posted. Kindly share your feedbacks. The next session will be starting by 7:25. So we can join by 7:25 in the same link. Thank you.
Thank you, Venkatesh, again.
Thank you, sir. Thank you, sir.